So basically we'll talk about nuclear fission, where larger nuclei or heavy nuclei overloaded with neutrons will break apart. And as they break apart, undergo fission, they also shoot out neutrons, neutral particles. Neutral particles are not bound by electromagnetic interaction to other particles, obviously, so they're most time free to fly out. So usually you have fission material at the end of the periodic table where elements are overloaded with neutrons. So now why would the heavy nuclei break apart like that? Well, there's a little story behind neutron. Neutrons, they like to be together with their buddies, neutrons and protons. If neutron is left alone, then neutron gets depressed and breaks apart. And I'm sure you're all familiar with this. This is called beta decay. Beta decay. So this is how you see it in chemistry class. That's how you should see it for real. So what do we have here? Let's see if we can zoom in. So neutron is neutral particle. So let's see, the charge will be, I think the charge is always on top. Let's see. Atomic number, atomic mass. Okay, charge is at the bottom. So this is a neutral particle with the mass number 1. This is a positively charged particle with the mass number 1. This is a negatively charged particle and -1. And then the mass number is 0, right? But it doesn't mean it has 0 mass. And this tiny little particle has lots of regalia, lots of things to be touched, like that. So in fact, it's a really, really tiny particle, low mass or no mass, we don't really know yet. And this is called electron anti-neutrino. Neutrino is an Italian word which stands for little neutron. Little neutron. So this idea was proposed by Enrico Fermi, an Italian scientist, in 1930s, I think, early 1930s, if not late 1920s. And he proposed that idea based on some experimental evidence, and then conducted calculations and basically predicted the energy output, and that coincided with the experimental evidence. So we will talk about this reaction multiple times. For now, just remember it's just beta decay. Beta minus decay. So what happens in this large nucleus? In this large nucleus, you may end up with a few neutrons next by. So neutron here, and this is by accident. That's what I meant when I said, it's an accident. It happens. We don't know why it happens. So neutron and neutrons and protons, they move around, you can say, and then they may end up piling up in one end with neutrons. And in this case, neutron to neutron attraction is absent, and neutron to proton attraction is absent. So protons will be somewhere on this end, and that means the so-called strong nuclear force is not able to hold on to a neutron, and a neutron left in that situation will undergo beta minus decay. And as a result, now we have too many protons. One is already too many, and basically what you have is positive charge, overall positive charge here, overall positive charge here, these things will repel each other and this will rip the nucleus apart. And as a result, bits and pieces are flying out, and neutrons being neutral, as I mentioned before, they will fly out as well. So one of the classical materials is uranium-235. So it will create all kinds of materials. So sometimes you see barium and krypton, sometimes you see other things. So we can just put one of those things. Let's see specifically. Let's put barium and krypton. Barium and krypton. Let's see this one maybe. Okay. So we have uranium-235, 92, 235. Sometimes you have to stimulate this process. Sometimes it happens accidentally. So basically, we're going to shoot a neutron. If you want to accelerate this process, shoot a neutron into this thing. So basically, you artificially overload this thing. In nature, it happens spontaneously, right? And uranium-235 is radioactive for that reason. So this will become krypton. The charge number is 36. The mass number is 92. It will also become barium. Barium, the mass number and the charge number is rather 56, and the mass number is 141. So now we have to see what else is left over. So the charge is balanced, and if you look at the mass, we have one from neutron over here. Let me just move the whole thing here. Just move it a little bit like that. So one from neutron, 235 from uranium-235. So it's altogether 236. 236, we have to subtract, this will be what, 233, right? So basically we end up with 3 particles, which will be neutral. Those are neutrons. So if these neutrons are absorbed by some other stuff, then that's the end of it. Nothing happens. If they are captured by the next, by uranium-235 nuclei next by, then they will also undergo fission reaction. So this is the basis for what's it called? Chain reaction, right? So when you have one nucleus breaks apart, shoots out neutrons, and that creates another one, and so forth. So that's called chain reaction. We'll go over this tomorrow. We'll talk about like a nuclear bomb or something like that. All right, so in this process, obviously, these particles fly out at a very high speed, so they have a lot of thermal energy, right? Neutrons either are captured and maintain fission reactions. So in case of nuclear power plants, you want to maintain the rate of reactions. You don't want it to accelerate, or you don't want it to die out. And so you have to kind of mitigate the number of neutrons. You have to have some material that will absorb neutrons so that the reaction will not become like a runaway reaction. Okay, so the kind of material that is used to absorb neutrons, so we call them neutron absorbing materials. Anything that has water would be a good absorber. So like plastics would work, but plastics have usually lower density. They also have carbon there. So this will work. Water is a good absorber of neutrons. Carbon, right? That's what actually people use. They use carbon rods to absorb neutrons. They still use them, but not on the industrial level. And I think aluminum, but I'm not 100% sure about that. So, but what we use today is primarily water. In the old days, people also used light water, or like heavy water rather, D2O. D2O, deuterium, is hydrogen with one neutron. So deuterium is basically equal to H1, 2. The mass number is 2 because it's made of one proton and one neutron. The nucleus is made of one proton, one neutron. That's called heavy hydrogen. And D2O is called heavy water. So let me write this down, heavy water. There's a famous story about Norwegian fighters who were assigned to destroy a heavy water facility that was built in Norway. And Germans were trying to take over that, and they were planning to use it to make nuclear bomb. So back then, that was the only way to use. D2O was the only kind of chemical that they could use in large quantities, produce in large quantities cheaply, and to be used to slow down neutrons. Okay, so this is a fission reaction. It produces heat. So what do? People use heat to turn into into electric power. So let's see how we do that. Let's see, next slide. Next slide. Let's go. So we have two kinds of reactors. Well, we have all kinds of reactors, right? But like two major ones. We have slow neutrons. So slow. So slow neutron reactor, and that's basically they also call sometimes thermal neutrons because they are really slow. And the good thing about this is that the likelihood of capturing these neutrons by other nuclei, uranium nuclei, is very high. The slower they move, the more likely that they will be captured. Now, how do we know that? We can relate it to what's it called? De Broglie wavelength. De Broglie wavelength is equal to H/mv, right? So the slower the neutrons, the larger they are, representing the wavelength, right? So in this case, basically delta will be the size of the neutron, essentially, right? And the larger it is, the more likely it will collide and be absorbed by a uranium nucleus. However, these slow neutron reactors, they produce a lot of waste. So the positive thing is that you can get energy easily in a way, but the bad thing is that they produce a lot of nasty waste. So they produce, I'll put the word nasty, radioactive waste, radioactive waste. It is waste because you cannot reuse it, you can't do anything with it. You have to bury it somewhere deep underground, or people used to dump these things into the oceans. They would seal the container and dump it into the ocean, hopefully like the deeper end of the ocean, and they would forget about that. So some models show that those containers are open, right? They basically salt water and motion eventually will break those containers, and then radioactive material will be released, and God knows what's happening at the bottom of the ocean where those containers were dropped. Another idea was to put this into the caves. One famous case, which is still ongoing, is to put them in a cave somewhere in, I think, Colorado or one of those southern states. The problem is that the container has to be intact for roughly 10,000 years. Who is there to guarantee that the mountain will not collapse, or the cave will not collapse, or will not be flooded in 10,000 years? Like, we don't know what's happening like in the next 4 years. So in the United States and most part of the world, reactors are obviously of this kind. Obviously, because this reactor is easier to build, cheaper, simpler, and you can just use water to generate heat, and then from heat you can generate electricity. So the basic idea behind this thing looks like this. You have radioactive material, which is called the core, and this core is surrounded by some sort of a container, right? This container there will be water coming in. So water will come in here. Oops, let me give you a different color. So water will come in here, right? And it becomes hot and comes out. Okay, so this is like the idea. So this container will be made of reinforced concrete, and it will have like a cap of something, a dome, and basically it could be opened for fixing or recharging everything. So this is uranium-235. 35. Enriched uranium, meaning that in real life, in nature, uranium is very rare, and the only few places where uranium is in higher concentration compared to like the background, and this is where people mine uranium. Even then, if you just pile up that uranium, nothing will happen. It may produce a little bit of heat, but not enough to make electricity. So they have to concentrate it, and they use chemical processes, and they also use centrifugal machines to refine uranium to about 2-3% of uranium in overall mix. So basically, uranium it comes in small pellets, right? And just like drugs, for example, when people take drugs, it says active ingredient, and you will notice that active ingredient is very tiny amount, and the rest is a filler. Filler means it's some sort of a neutral material that will be either digested, like sugar kind of stuff, or it will be like neutral mineral which will not be digested, which won't be used by the body. So, but the active ingredient will become the medicine that the doctor prescribed. In this case, 2-3% is active ingredient. 2-3% is uranium-235. The rest is basically oxygen and some other minerals that come along with these pellets. So these pellets are roughly the size of a dime, and they're kind of round shape, I think. As far as I remember, we went to this place in New York upstate, to the nuclear power station, and they showed us pictures of those things. They didn't show those pellets themselves. And they are loaded into the tubes, metal tubes. I'm not sure if aluminum, but like some kind of metal tubes. They're sealed, and when they're brought to the facility, they are not active. So then some government person comes from the federal government with a special suitcase which shoots neutrons, and they shoot neutrons at this tube, and then after that the chain reaction starts and it reaches certain equilibrium, and that's it. You cannot stop this thing. Once you started it, you cannot stop it. And then these rods are then lowered into the pool of water. So basically this is a pool of water, and that's how you keep them cool. And they also have they used to have rods that would slow down the reaction and basically bring it to stop. I think this time they use water. So this rods will be in the water, which will cool them and also will reduce number of neutrons substantially. Okay, so the way this thing works is that they don't want you to use this water because this water eventually becomes radioactive. They don't want to use this water to produce electricity. What they do is they run this through the coil, that will heat another water. So this is the coil, this is the flow of the water, and we have another coil where we have water coming in from here and going like this. Almost looks like a transformer. So what happens here is this water turns into steam. The water coming in the primary coil will be, temperature will be roughly, I'm going to make up some number. I hope I'm right. 300 degrees Celsius. And also it's going to be high pressure. Right? So this way it doesn't allow it to boil, I think. And then what happens with the secondary coil, you get steam as a result of heating the water in the secondary coil. So this is water, and that goes into steam. Okay, and that's what we do. We like to heat the water to turn into steam, and the steam will then produce electricity because it will start turning the turbine. So here you have a turbine. I'm just making it like a propeller. So steam will basically push the turbine, and the turbine will rotate, and here we get electricity. So we get plus, minus. Okay, a very simplified kind of schematics. So that's how we produce electricity. It's not cheap because the construction of the power station is pretty expensive process. Takes a long time. The United States is no longer producing its own reactors. So the reactors, like George W. Bush was trying to promote nuclear power at a certain point, and they couldn't do anything because they had to buy reactors from Japan, and Japan doesn't make a lot of reactors. You have to kind of pre-order, and then it takes about 10 years to build a nuclear power station. Very intense in terms of investment, time-consuming, construction, and at the end, electricity costs slightly more than hydropower. Slightly more than hydropower, but coal is cheaper and people keep on using coal for some reason. Anyways, so that's the slow neutron reactor. The problem again is it produces lots of waste. And the second type of reactor, which I know is employed in France, and it was, I think it was a regional kind of thing, is fast neutron reactor. So fast neutron reactor it's more complex. It's more complex. So it requires more, intelligence, I suppose. And it has multiple loops, not just one or two loops, multiple loops. And they use, for the cooling of the reactor, they actually use sodium metal. So sodium metal is used to cool the reactor. So then you have the sodium metal that will melt, right? And it doesn't boil up to a pretty high temperature. So basically what you have here is sodium, which is the primary coil, right? And then you have water being heated and turned into steam. Right? And then this could be used, or they may have even another coil that is going here. And then you have the third coil that will actually be running the turbine. So that's already pretty complicated, and sodium metal has to be handled very carefully because as it's liquid, it will try to dissolve other metals within it to forming alloys. So they have to have certain ways, I don't know about that, ways to make sure that the sodium would not eat into the other metal components of the reactor. Even though this is more complicated, the outcome is much better. It's actually pretty rewarding to have this kind of reactor, because what you have here is the waste is no longer waste. The waste basically becomes generates feasible material. So waste, oops, hold on 1 second. So waste is feasible, I'm sure that's how we spell it, feasible material. What it means is that the waste becomes fuel in itself, okay? And then you can take that and then put it in another reactor, and then continue getting more heat out of the material. And this way, first of all, you reduce the actual waste at the end. Second of all, you're getting more energy from the same, basically double the amount of energy from the same amount of uranium-235. And again, I'm not sure the 235 or 238, they use some kind of different, probably uranium. But anyways, this is more like progressive. And as far as I know, in France, they have this kind of reactors. I'm not sure about Germany, but in France, they do have this kind of reactors. Okay, that should be enough. Any questions? Any questions?